Welcome to the lecture series on engineering mathematics. In this lecture, we talk about solutions of linear differential equations with constant quotients. In the previous lecture, we have seen the general form of differential equations and classification of differential equations and the most general form of linear differential equation with constant quotients. In this lecture, we focus on solution types. The general form is given by the nth derivative of y plus a1 times n minus 1th derivative of y, so on, so on. An y is equal to 0 is the homogeneous linear differential equation with constant quotients. If y is equal to e power mx is a solution, then it has to satisfy the given equation. So by calculating the derivatives and substitution, we can observe that m power n plus a1 m power n minus 1 so on an into e power mx is equal to 0 on substitution. Since e power mx can never be 0, the auxiliary equation has to be satisfied. That is m power n plus a1 into m power n minus 1 so on an is equal to 0. So then for different values of m, n number of roots may exist, and for all n values of m, the solutions may exist. So if I solve the auxiliary equation, we will get n roots of the auxiliary equation, and for those n number of values of m, we will have the solutions. Given auxiliary equation, there are n number of roots, and we know how to solve algebraic equations. Once we solve, there are three possibilities. Either the roots may be real and distinct, or roots may be equal, and roots may be complex conjugate, or a combination of these things. For the sake of simplicity, we will focus on second order algebraic equation of the form m square plus am plus b is equal to 0. Then in the first case, if the roots are real and distinct, let m1, m2 be the roots, and m1 is not equal to m2. In this case, y1 is equal to c1 e power m1x and y is equal to c2 e power m2x are the solutions, because the general solution is assumed to be y is equal to e power mx, and we have solved the auxiliary equation m1, m2 are the roots. Then by the property of linear differential equation, any linear combination of the solutions is also a solution, which is the general form. So y is equal to c1 e power m1x plus c2 e power m2x is the most general solution for the given differential equation when the roots are real and distinct. Now if m1 is equal to m2, then here is an interesting observation is there. We can observe that d minus m into e power mx is equal to 0. If I find the derivative, it cancels out. So e power mx is a solution for ordinary differential equation of first order. When it comes to d minus m square, that means m is a repeated root. In this case, m is a repeated root. D minus m square into x e power mx. If you observe, it can be written as d minus m into d minus m of x into e power mx, so that the inner part of d minus m can be applied on x e power x. So m into x into e power mx plus e power mx minus m into e power mx. So they cancel out and reduces to d minus m into e power mx, which is already 0 by the above case. So by this observation, we have the result that x e power mx is also a solution apart from e power mx, since m being a repeated root. So the general form is c1 e power mx, c1 e power mx plus c2 times x e power mx is also a solution. For the given auxiliary equation, if there may be k number of repeated roots, in this case, again by following the above observation, we have the most general solution as c1 plus c2x plus c2x, c3x square, so on ck x power k minus 1 times e power mx is a solution, most general form, if the root has repeated k number of times. The third case is the roots are complex conjugate. The roots may be of the form alpha plus or minus I beta. That means two roots are there, alpha plus I beta, and alpha minus I beta. So the general solution should be in the form of c1 e power alpha plus I beta x plus c2 e power alpha minus I beta x. If we take alpha e power alpha x as common, we can write it as c1 I beta x. So since e power I theta is equal to cos theta plus I sin theta can be used here, and it reduces to c1 cos beta x plus c2 sin beta x multiplied with e power alpha x. Now, if again the complex conjugate roots may also be repeated, in that case, we'll have e power alpha x into c1 plus c2x times cos beta x plus c3 plus c4x times sin beta x will be the solution if complex conjugate roots repeated. So this is how the three cases can be observed, and given any numerical problem, we can solve the algebraic equation, obtain the roots, and based on the three cases, we can write the solution.